Welcome to this problem walkthrough. Today, we'll be solving problem number 815, titled Bus Routes. This is a fascinating problem that challenges your understanding of graph traversal and optimization techniques. Let's dive right in. In this problem, we are tasked with finding the minimum number of buses needed to travel from a given starting bus stop, called the source, to a destination bus stop, called the target. The input is an array called routes, where each element represents a bus route, and the integers within each route represent the stops that bus serves. For example, if routes 0 is 1, 2, 7, it means the first bus, or bus 0, stops at bus stops 1, 2, and 7. Along with this, we are given two integers, source, the starting bus stop, and target, the destination bus stop. Our goal is to figure out how many buses we need to take to get from the source to the target. If it's not possible to reach the target from the source using the given routes, the function should return -1. To solve this, we need to account for the constraints, such as the number of routes, the number of stops in each route, and the range of the bus stop IDs. To better understand the problem, let's look at an example. Suppose we have routes equals 1, 2, 7, 3, 6, 7, source equals 1, and target equals 6. Here's how we would navigate. We start at bus stop 1. From there, we can take the 0th bus, which travels through stops 1, 2, and 7, to reach stop 7. From stop 7, we can then switch to the 1th bus, which travels through stops 3, 6, and 7, to reach stop 6. In total, we use 2 buses to get from stop 1 to stop 6. Therefore, the output is 2. Now let's consider a second example. Here, routes equals 7, 12, 4, 5, 15, 6, 15, 19, 9, 12, 13, source equals 15, and target equals 12. In this case, it's not possible to travel from stop 15 to stop 12 using the given bus routes. No combination of buses connects these two stops. Therefore, the output is -1. This highlights that the problem isn't just about finding any path but determining whether a valid path exists at all. In a third example, we have routes equals 2, 8, 15, 9, 15, 20, 8, 9, 10, source equals 2, and target equals 20. Starting at stop 2, we can take the 0th bus to reach stop 15. From stop 15, we transfer to the 1th bus, which takes us to stop 9. Finally, from stop 9, we can take the 2nd bus to reach stop 20. In total, we use 3 buses to complete this journey. Hence, the output is 3. There are several constraints and edge cases to consider while solving this problem. First, if the source and target are the same, no buses are needed, so the output should be 0. Second, if there's no path connecting the source and target, the output should be -1. Third, because the input size allows for a large number of routes and stops, the solution must be efficient to handle cases with up to 500 routes, each containing up to 100,000 stops. Lastly, different routes may share some bus stops, and this overlap is crucial for determining the shortest path. Efficiently handling these overlaps is key to finding the correct solution within the given constraints. To tackle the bus routes problem, we first consider the brute force approach. The intuition here is straightforward: simulate all possible bus routes and stops to check if there's a path from the source to the target. Starting from the source stop, we manually evaluate each bus route to see if it passes through the source and eventually reaches the target. However, this approach quickly becomes inefficient as we iterate through all routes and stops. A few key observations stand out. Each bus route is essentially a list of stops, and multiple bus routes can overlap at certain stops. This overlap is essential because it allows us to transfer between buses. To solve the problem efficiently, we need to minimize the number of bus transfers. Unfortunately, with a time complexity of n², where n represents the total number of stops, this brute force method becomes impractical for large datasets, such as when routes include thousands of stops. Recognizing this inefficiency, we pivot towards a more structured and scalable solution, a graph-based approach. Here, we model the problem as a graph traversal task to find the shortest path between the source and target stops. In the graph-based approach, we represent the problem in a way that directly aligns with graph traversal techniques. Each bus stop becomes a node, and edges are created between stops that share a common bus route. The shortest path in this graph corresponds to the fewest number of bus transfers, which is exactly what we're trying to minimize. To solve this, we use breadth-first search, or BFS, which is ideal for unweighted graphs. BFS ensures that we explore all possible paths level by level, guaranteeing that the first time we reach the target stop, it's via the shortest path in terms of transfers. A key insight here is that instead of explicitly building a graph where stops are the nodes, we can optimize further by treating entire bus routes as nodes. In this abstraction, connectivity between routes is determined by shared bus stops. This shift reduces redundancy and makes the graph simpler to navigate. The time complexity for this approach, O, n plus e, where n is the number of bus routes and e is the number of connections, demonstrates its efficiency. Similarly, the space complexity is manageable, also O, n plus e, accounting for both the graph representation and the visited nodes during traversal. Ultimately, we chose the graph-based approach due to its balance of efficiency and clarity. By treating bus routes as nodes and leveraging BFS, we focus directly on minimizing transfers without unnecessary computations. While the brute force method might be easier to implement for small cases, it becomes infeasible as the input size grows. The graph-based approach, on the other hand, includes a pre-processing step to efficiently represent routes and stops, but this upfront cost is significantly outweighed by the runtime savings during BFS traversal. The trade-offs between the two approaches are clear. Brute force is conceptually simple but computationally expensive, whereas the graph-based method is slightly more complex in setup but scales effectively for large inputs. The key insight, or the aha moment, came from realizing that bus routes themselves could be treated as nodes in the graph, with shared stops forming edges. This abstraction not only simplified the problem but also allowed us to apply BFS efficiently, ensuring an optimal and scalable solution to the problem at hand. To solve the bus routes problem, the first step is to understand the context. The challenge is to navigate a public transit system efficiently, minimizing the number of bus transfers needed to get from a source stop to a target stop. The input consists of bus routes, where each route lists the stops covered by a particular bus. The key idea is to model this problem as a graph, where bus stops represent nodes, and two nodes are connected if they share the same bus route. This framing allows us to interpret the task as finding the shortest path in an unweighted graph. To achieve this, we use breadth-first search, or BFS, which is well suited for shortest path problems in unweighted graphs because it explores all nodes at the current depth before moving deeper. However, before running BFS, we need to pre-process the data. Specifically, we create a stop_to_routes mapping, where each bus stop is a key, and the value is a list of all the routes that pass through that stop. This pre-processing helps us efficiently access relevant routes as we traverse the graph. With the stop_to_routes mapping prepared, we initialize the BFS algorithm. We use a queue to manage the traversal state, where each entry stores the current bus stop and the number of transfers made so far. To avoid redundant processing, we maintain two sets, visited_stops to track stops we've already processed, and visited_routes to ensure we don't revisit the same bus route multiple times. BFS begins at the source stop, which is enqueued with 0 transfers. This stop is immediately marked as visited. During traversal, we dequeue the front element, representing the current stop and transfer count. For each bus route passing through the current stop, we check if the route has already been visited. If not, we mark the route as visited and proceed to examine all the stops on that route. If any stop matches the target, we return the transfer count +1, as we've reached the destination. This step ensures that the shortest path is identified as soon as the target is found. If a stop on the current route doesn't match the target and hasn't already been visited, we enqueue it with an increment transfer count and mark it as visited. This ensures that BFS explores all possible paths in the most efficient way. There are also critical edge cases to handle. If the source stop is the same as the target, no buses are needed, so we immediately return 0. On the other hand, if there's no possible route connecting the source and target, the result should be -1, indicating that the destination is unreachable. Once BFS finishes traversing all possible paths without finding the target, we return -1 as well. These conditions ensure the algorithm handles all scenarios robustly. The key insights of this solution are in the graph representation, BFS efficiency, and data preprocessing. Modeling bus stops as graph nodes and bus routes as connections allows us to leverage BFS to find the shortest path. By avoiding redundant processing with visited_stops and visited_routes, we optimize runtime. Finally, pre-processing with the stop_to_routes map ensures that route lookups during traversal are efficient, keeping the algorithm scalable. Now let's look at the specific data structures that power this approach. First, we use a queue for BFS, where each element is a pair of the current stop and the number of transfers made. This enables a level-by-level traversal of our graph. Next, we use a set called visited_stops to track stops that have already been processed. This prevents cycles and avoids redundant processing, ensuring that we don't revisit the same stop multiple times. Similarly, we use another set called visited_routes to ensure that each bus route is processed only once. This prevents unnecessary computations and keeps the traversal efficient. Finally, we use a dictionary called stop_to_routes to map each bus stop to the list of bus routes passing through it. This structure is critical for efficient lookups during BFS, as it allows us to quickly identify all the routes available from any given stop. These data structures work together to streamline the traversal and ensure the algorithm performs effectively even for large inputs. Here's how the algorithm is implemented in Python. After importing the required libraries, we define the function number_buses_to_destination. The first step checks if the source and target are the same. If they are, we return 0 immediately, as no buses are needed. Next, we pre-process the input data to build the stop_to_routes mapping using a default dict. For each route, we iterate over its stops and append the route index to the list of routes for that stop. This pre-processing step allows us to efficiently query which routes pass through any given stop. Following that, we initialize BFS with a queue containing the source stop and a transfer count of 0. We also initialize the visited_stops set with the source stop and an empty visited_routes set. Then, we begin the BFS traversal. While there are elements in the queue, we dequeue the front element to get the current stop and the number of transfers made so far. For each route passing through the current stop, we check if the route has already been visited. If it hasn't, we mark it as visited and proceed to evaluate all the stops on that route. For each stop on the current route, if it matches the target stop, we immediately return the current transfer count +1, as we found the shortest path to the destination. If the stop hasn't been visited yet, we mark it as visited and enqueue it with an increment transfer count. This ensures that BFS continues exploring other paths while maintaining the shortest path guarantee. If the algorithm exhausts all possible paths without reaching the target stop, we return -1 to indicate that the destination is unreachable. Now let's consider an example to see how this works in practice. Suppose the input consists of two bus routes, 1, 2, 7, and 3, 6, 7, with a source stop of 1 and a target stop of 6. The goal is to determine the minimum number of bus transfers required to travel between these stops. The first step is to pre-process the data by building the stop_to_routes mapping. For this example, the resulting mapping is 1, 0, 2, 0, 7, 0, 1, 3, 1, 6, 1. This shows which routes are accessible from each stop, making it easy to reference during traversal. Next, BFS is initialized with the queue set to 1, 0, indicating that we start at stop 1 with 0 transfers. The visited_stops set is initialized to 1, and the visited_routes set is empty. During traversal, the first element, 1, 0, is dequeued. From stop 1, we access route 0, which includes stops 1, 2, 7. Stops 2 and 7 are added to the queue with 1 transfer, and the visited_stops set becomes 1, 2, 7, while the visited_routes set becomes 0. The next stop, 2, 1, is dequeued but doesn't lead to the target. Then, stop 7, 1, is dequeued. From stop 7, we access route 1, which includes stops 3, 6, 7. Stops 3 and 6 are added to the queue with 2 transfers. The visited_stops set is updated to 1, 2, 7, 3, 6, and visited_routes becomes 0, 1. Finally, stop 6, 2, is dequeued, which matches the target. The algorithm returns 2, indicating that 2 transfers are required. This example demonstrates how the algorithm efficiently finds the shortest path using BFS. Here, we begin the Python implementation by importing the necessary modules, deque from collections for our queue and defaultDict to create a mapping of stops to routes. Inside the solution class, we define the number buses to destination function, which takes three parameters: routes, source, and target. The first condition checks if the source and target stops are the same. If they are, no buses are needed, so we return 0 immediately. Next, we create a mapping called stop_to_routes, which associates each bus stop with all the routes that pass through it. This is done using a nested loop where we iterate over each route and its stops, appending the route index to the list of routes for each stop. Now, we initialize our breadth-first search, BFS. We use three main structures: visited_stops to track the stops we've already processed, visited_routes to track the bus routes we've already taken, and a queue, which will hold tuples of the current stop and the number of buses taken so far. The source stop is added to visited_stops, and we enqueue it with a count of 0 buses. As the BFS loop begins, we dequeue the first item to get the current stop and the count of buses taken so far. For the current stop, we retrieve all the routes that pass through it using the stop_to_routes mapping. If a route has already been visited, we skip it. Otherwise, we mark the route as visited to ensure we don't process it again. Then, for each stop in the current route, we check if it matches the target. If it does, we return the number of buses taken so far, +1, because we've successfully reached the destination. If the stop hasn't been visited yet, we add it to visited_stops and enqueue it with an increment bus count. This ensures that we explore all possible stops reachable from the current route. Finally, if the queue becomes empty and we haven't returned a result, it means there's no way to reach the target stop, so we return -1 to indicate it's not possible to complete the journey. Here, we start by importing the necessary libraries and defining our solution class. The method number buses to destination takes three parameters: an array of bus routes, a source stop, and a target stop. First, we handle the edge case where the source and target are the same by returning 0, as no buses are needed. Next, we construct a map, stop_to_routes, which maps each bus stop to a list of routes that pass through it. This is essential for efficiently determining which routes are accessible from a given stop. We use a nested loop, iterating through each route and its stops, and populate this map using the computeIfAbsent method to simplify the logic for adding entries. Then, we initialize the BFS algorithm. We'll use a queue to track the current stop and the number of buses taken so far. Additionally, we maintain two sets: visited stops to prevent revisiting the same stops and visited routes to avoid redundant processing of routes. The source stop is added to the visited stops set, and we enqueue it in the BFS queue with an initial bus count of 0. The main BFS loop begins, where we repeatedly process elements from the queue until it's empty. Within the BFS loop, we first extract the current stop and the number of buses taken so far. For each route accessible from the current stop, we skip it if it has already been visited. Otherwise, we mark the route as visited. Then, we iterate through all stops in that route. If we find the target stop, we immediately return the number of buses taken +1, as we've successfully reached the destination. If the stop hasn't been visited yet, we mark it as visited, and enqueue it with an increment bus count to continue the search. This ensures we explore all possible paths while minimizing the buses taken. If the queue is exhausted without finding the target, we return -1 to indicate that the destination is unreachable. This implementation uses BFS to guarantee the shortest path in terms of buses taken, leveraging the stop-to-routes map for efficient traversal between stops and routes. To solve this problem, we start by initializing some key data structures. The stop_to_routes map helps us quickly find which bus routes are associated with each stop. For this example, stop 1 is part of route 0, stop 7 is part of both routes 0 and 1, and so on. We also maintain a set of visited_stops, starting with the source stop, which is 1. Similarly, visited_routes tracks which bus routes we've already used, and it starts empty. Finally, we initialize the queue for our breadth-first search, starting with the source stop and a count of 0 buses taken. In the first BFS iteration, we dequeue stop 1, which is our starting point, and check all routes passing through it. Route 0 is unvisited, so we mark it as visited and explore all stops in this route. Stop 1 is already visited, but stops 2 and 7 are not, so we enqueue them with an updated bus count of 1. Our queue now contains stops 2 and 7, each reached using one bus. In the second BFS iteration, we process stop 2, where one bus has been taken to reach it. The only route passing through stop 2 is route 0, which has already been visited, so there's nothing more to do here, and we move on. Next, we dequeue stop 7, which was also reached using one bus. Stop 7 is part of two routes, route 0, which is already visited, and route 1, which is unvisited. We mark route 1 as visited and explore its stops. Stop 3 is not visited, so we enqueue it with an updated bus count of 2. Stop 6 is also part of route 1, and since it is our target stop, we immediately return 2 as the number of buses required to get from the source to the target. This concludes the first example, where the output is 2. Now, for the second example, we begin again with initialization. The stop_to_routes map shows which routes each stop belongs to, and it's structured to include overlapping routes like stop 3, which is part of both routes 0 and 1. We start with visited_stops containing the source stop, which is 1, and an empty visited_routes. The queue is initialized to begin BFS from stop 1 with 0 buses taken. In the first BFS iteration, we dequeue stop 1 and examine all routes passing through it. Only route 0 applies, so we mark it as visited and explore its stops. Stops 2 and 3 are unvisited, so we enqueue both with a bus count of 1. The queue now contains stops 2 and 3, each reached using one bus. Next, we process stop 2, where one bus has been taken to reach it. The only route passing through stop 2 is route 0, which has already been visited, so we move on. Now, we dequeue stop 3, also reached with one bus. Stop 3 is part of two routes, route 0, which is already visited, and route 1, which is unvisited. We mark route 1 as visited and explore its stops. Stop 4 is unvisited, so we enqueue it with a bus count of 2. Similarly, stop 5 is unvisited, so we enqueue it with the same bus count. At this point, the queue contains stops 4 and 5, each reached using 2 buses. Finally, for stop 4, the only route passing through it is route 1, which is already visited, so we continue. Now, we process stop 5, where 2 buses have been taken to reach it. Stop 5 is part of 2 routes, route 1, which is already visited, and route 2, which is unvisited. We mark route 2 as visited and explore its stops. Stop 6 is unvisited, so we enqueue it with a bus count of 3. Stop 7, our target stop, is also part of route 2. Since we've reached our target, we return 3 as the number of buses required. This completes the second example, where the output is 3. For the third example, we initialize the stop_to_routes map, which associates each stop with its corresponding routes. Stops 1, 2, and 3 belong to route 0, while stops 4, 5, and 6 belong to route 1. The visited_stops set starts with the source stop, 1, and visited_routes is empty. The queue starts with stop 1 and 0 buses taken. In the first BFS iteration, we dequeue stop 1 and examine the routes passing through it. Only route 0 applies, so we mark it as visited and explore its stops. Stop 2 is unvisited, so we enqueue it with a bus count of 1. Similarly, stop 3 is unvisited, so we enqueue it with the same bus count. The queue now contains stops 2 and 3, each reached using one bus. However, in the second BFS iteration, we process stop 2, and no further routes lead to the target. At this point, the BFS exhausts all possibilities, and since we never reach stop 6, we conclude that the target is unreachable. The output for this example is -1. To analyze the time complexity, we start by considering the process of building the stop_to_routes dictionary. This involves iterating through all the bus routes and their respective stops. If there are n routes and each route has an average of k stops, the total number of stops across all routes is approximately n*k. Since we construct the dictionary by mapping each stop to the list of routes that pass through it, this step takes n*k time. Next, we examine the breadth first search, or BFS, which is used to find the shortest path from the source stop to the target stop. In the worst-case scenario, the algorithm might need to traverse every stop and every route. Because each stop is visited at most once, and for each stop, we check all the routes that pass through it, this traversal also takes O and *k time. Therefore, combining these components, the overall time complexity of the solution is O and *k. Now, for space complexity, we begin with the stop_to_routes dictionary. This data structure maps each stop to the routes that pass through it. In the worst case, where all n routes pass through all k stops, the dictionary requires O and *k space. Next, we consider the visited sets, visited_stops and visited_routes. The visited_stop set keeps track of all the stops that have been visited during the BFS traversal, and in the worst case, it could contain up to n*k entries, requiring O and *k space. The visited_routes set stores the routes that have been visited, and since there are at most n routes, its space requirement is O, n. Additionally, the BFS queue, which temporarily stores stops for exploration, can hold all stops in the worst case, needing O and *k space. When we combine all these components, the overall space complexity is also O and *k. To put this into perspective, let's compare this approach with a naive solution. A naive approach might involve evaluating all possible combinations of bus routes to find the minimum number of buses required. This would lead to factorial or exponential time complexity in the number of routes, making it impractical for large datasets. In contrast, our optimized solution uses BFS to efficiently find the shortest path, minimizing the number of buses needed. By utilizing the stop_to_routes mapping, we avoid redundant computations and focus only on relevant stops and routes. This keeps both the time and space complexities linear in relation to the total number of routes and stops, which makes the solution scalable. Breaking it down further, the best-case scenario occurs when the source and target stops are the same, requiring only O(1) time and space. In an average case, the BFS explores a portion of the routes and stops before locating the target, often resulting in sublinear exploration relative to the total input. However, in the worst case, where no efficient connection exists, all routes and stops are traversed, leading to O and *k time and space complexity. When solving problems like bus routes, there are some common mistakes to watch out for. First, overlooking edge cases is a frequent issue. For example, failing to handle situations like empty inputs, single-element arrays, or invalid ranges can result in runtime errors or incorrect outputs. To avoid this, it's important to test your code with edge cases, such as the minimum and maximum constraints specified in the problem. Next, ignoring time complexity can also be problematic. If you rely on an inefficient brute force solution without considering the input size constraints, you may run into TLE, or time limit exceeded, errors for larger inputs. To prevent this, analyze the time complexity of your approach early on and optimize as needed. Lastly, making incorrect assumptions about the input is another common pitfall. For instance, assuming the input is sorted or contains unique elements when the problem doesn't explicitly state so can lead to flawed logic and missed edge cases. Always read the problem statement carefully to avoid making these assumptions. Another common mistake is failing to validate intermediate results during your solution. For example, skipping checks on intermediate calculations, such as ensuring array indices remain in bounds or that variable ranges are valid, can lead to errors or invalid results. To mitigate this, you can use debug prints or assertions to verify the correctness of intermediate values. Additionally, poor handling of data structures can cause inefficiencies or logical errors. For instance, using a list when a set would be more appropriate can unnecessarily increase complexity. A set, for example, offers faster lookups compared to a list. To address this, choose your data structures based on the specific operations required by the problem. For example, if you need fast lookups, a set or dictionary might be the better choice, while a queue could be ideal for BFS operations. In interviews, it's not just about getting the correct solution, how you communicate your approach matters a lot. Focus on clarity when explaining your thought process. Even if your first attempt isn't optimized, interviewers appreciate clear reasoning and the ability to refine your solution. Start with a brute force approach and then discuss its limitations, gradually improving it to something more efficient. Using examples is also highly effective. Walk through small test cases to validate your logic and demonstrate your understanding of the problem. Additionally, highlight any trade-offs you're making, such as using extra space to improve time complexity, and show an awareness of edge cases by mentioning them upfront. Related problems can also offer valuable insights. For instance, binary tree-level order traversal, LeetCode 102, focuses on BFS traversal, while Rotting Oranges, LeetCode 994, introduces time-based state changes. Course Schedule 2, LeetCode 210, involves topological sorting, and the bus routes problem itself is a graph problem requiring BFS to find the shortest path under specific constraints. Finally, let's look at some alternative approaches you can use for problems like this. Breadth-first search, or BFS, is a go-to method for shortest path problems in unweighted graphs. It's time-efficient but does require extra space for the queue. Depth-first search, or DFS, is another option, typically used for exhaustive traversal or pathfinding in weighted graphs. However, it can lead to stack overflow in cases of deep recursion and is less suitable for shortest path problems. For weighted graphs specifically, Dijkstra's algorithm is a great option for finding the shortest path. While it's effective, it's more complex to implement and slower than BFS for unweighted graphs. Lastly, bidirectional search is an advanced technique where you perform BFS from both the source and target nodes, significantly reducing the search space. However, it does require additional memory to keep track of both search frontiers. Each of these approaches has its own trade-offs, so it's important to choose the one that fits the problem's requirements best. Great job on completing this problem walkthrough. To summarize, we tackled problem number 815, learned about graph traversal techniques, and understood the importance of BFS in optimizing solutions. Keep practicing and applying these concepts to similar problems. Thank you for watching, and don't forget to like and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!